Like to share about the chapter 7, which is transverse shear. So this is our first questions. If the wide flange beam is subjected to a shear force of V equal to 20 kilonewton, determine the shear stress on the web at A. Indicate the shear stress component on a volume element located at this point. So this is the picture. Okay, we can see at this I-beam is symmetry. So we know that the natural axis is at the center of the I-beam here. Y bar is measures from the natural axis to the centroid of element. So we get the Y bar is equal to 116 millimeter. Okay, first of all, we need to find the moment of inertia of the cross section about the natural axis. So it is indicated by I, and it is because this is a rectangle, so we use 1/12 BH cube for the I. So here is 1/12 BH cube here, and for this element, so we plus with 2 times 1/12 0.2 times 0.02 cube plus area times Y bar. This we times with 2 because we have two elements with same dimension. So we get the answer is 0.2501 to the 10 to the power of -3 meter power of 4. So from figure A, we get the QA is equal to Y bar times area. The Y bar is 0.16 times 0.02 times 0.2. So we get 0.64 times 10 to the power of -3 meter cube. So we move to the applying the shear formula. Shear formula is equal to V times QA over IT. V is a shear force which given from the equation, from the questions. Q we get here, we get from here, and the I we calculate before, and T is the thickness. So substitute all, and we got 2.56 megapascal. So the shear stress component at A is represented by the volume element shown in figure B. We take from the natural axis to the top, so we get this one. This size Y bar is equal to 0.16 meter, and the distance from the natural axis to here is 0.15. A is located here, so the volume element here we can see at this figure B. This is the shear stress. Shear stress is a parallel force acting on an element. So this is shear force. So we get shear force is equal to 2.56 megapascal. That's all. Thank you.
Okay, I take this question from Pearson 9 edition, Mechanic of Material, page 378. Question number 2. Okay, the question is, if the wide flange beam is subjected to a shear of 20 kN, determine the maximum shear stress in the beam. So as you can see in the question, we have to find the maximum shear stress of this beam. This beam is given. And so the formula for maximum shear stress is VQ over IT, whereas the value of V is given, and so we have to find the Qmax and I. In order to find the Qmax and I mean moment of inertia, I draw a new figure which of the beam. We started from the neutral axis, and so let's find the moment of inertia. This is the calculation, and the value of the moment of inertia of the wide flange beam is 0.2501. Multiply the 10 to the power of -3, and to find the Qmax, use this formula, which can be found in the figure that I draw. Basically 0.02 multiply with 0.2 and then multiply with 0.16 plus 0.02 multiply with 0.075 multiply with 0.15 and you will get the answer, which is 0.865 multiply 10 to the power of negative 3. With that, we can find the maximum shear stress, which is 3.459 megapascal. Thank you.
Today, I would like to discuss about Chapter 7, Transverse Shear Stress. Question given: determine the maximum shear stress acting at section AA of the cantilever strap. This is the cantilever strap, section AA. First, we know that maximum shear stress, given the formula tau maximum equals to V Q maximum over IT. To find the V, we first need to know the shear stress at section AA. Okay. From the free body diagram, total Fy equals to 0. We assume outside is positive. V minus 2 kilonewton minus 4 kilonewton equals to 0. Then we get the V equals to 6 kilonewton, also equals to 6,000 Newton. Next, we have to know the Q maximum. Formula for Q maximum is Y prime bar times A prime. To find the Y prime bar, we have to know the Y bar first. Formula of Y bar is total Y bar area over total area. Okay. First, we have to know Y bar for each section in this strap. Y bar for this section is half of the 20, means 10 times area of 50 times 20, plus this section, half of the 70 is 35, plus 20 from here to here, and then times the area of 20 times 70, divided with 50 times 20 of this area plus 20 times 70. We get the answer for Y bar is 36.25. Next, to find the Y prime bar, which means this shaded region area, Y prime bar is somewhere around here. To find this area and this distance, we have to 90 the total height of this strap minus Y bar, get this, and divide by 2 half of this section. We get the answer is 26.875. Next, we calculate Q maximum. We get the answer 26.875 for the Y prime bar, and then times with the A prime, area of this section, shaded region, 20 times this height, we get from here 53.75, and then we get the Q maximum is 28890.625. We get the answer Q maximum equals to 28890.625. Next, we have to find the value of I, moment of inertia. The equation given is BH power of 3 over 12 plus a y bar power of 2. For this section, we get 50 times 20 power of 3 over 12 plus area 50 times 20 times the half from here to the neutral axis, means y bar minus 10. For this section, 20 times 70 power of 3 over 12 plus 20 times 70 times here to here, here to the neutral axis, means 35 half of the 70 plus 20 minus neutral axis y bar. We get I equals to 1786,250. T, we know that it is the width of this shaded region, means 20 millimeter. Finally, we can get the tau max by substitute all the value inside. We get final answer is 4.85 Newton per millimeter square, or also 4.85 megapascal.
Determine the shear stress at point B at cross-section AA. So, to calculate this question, we need to find the shear stress of this cross-section AA. So this one is the cross-section of the beam, of the cantilever beam. So, to calculate the shear stress, we need to use this formula. Tau equals to VQ over IT, where tau is equals to shear stress, V is equals to shear force, I moment of inertia, T is equals to width of the member's cross-sectional area measured at the point where tau is to be determined, and Q is equals to y bar prime multiplied by A prime. Okay, so first of all, we need to find our shear stress, this one. This one. So, to calculate the shear stress, we need to draw the free body diagram of this beam. So this one is the free body diagram because after we only need to draw after the cross section of this beam. So this one is actually at point AA. So we need to use we need to find our shear force. So we need to use this one. Total Fy, Fy is vertical forces, equals to 0, where we assume going up is positive. So Fay, this one is Fay, we assume is going up, so it's positive, minus 2 kilonewton because negative because it's going down, and minus 4 kilonewton because negative because it is also going down, equals to 0. So Fay, after we calculate it, Fay equals to 6 kilonewton. So this one is our shear force. So our shear force is 6 kilonewton. Okay, the second one we need to find is our centroid. So to find centroid, we need to use y bar is equals to total area multiplied by the centroid divided by total area. So we take a look at this diagram. So this one is area 1, this one is area 2. We divide it like this, So for area 1, the formula, the calculation is like this. 0.02 This one I already converted to meter. 0.02, which is also equals to 20 millimeter. This one is in meter. Multiply by 0.07, 0.07, 70 millimeter. Multiply by the centroid of this area. So the centroid of this area is 70 divided by 2, which is equal to 35 millimeter. So the centroid is at here. But we need, but 35 millimeter is from here to here. So we need to add another 20. So because we need to calculate it from the bottom to the centroid of the area. So 35 plus 20 is equals to 55 millimeter. So 55 millimeter, which is also equals to 0.055 meter. So 0.055 meter is this one. So we need to plus for area 2. So it's 0.02, 20 millimeter, 0.05, 50 millimeter, this one, and the centroid of this rectangle, so which is 20 divided by 2 is 10 millimeter, which is also equals to 0.01 meter, divided by the area of area 1 and area 2, 0.02 multiplied by 0.07 plus 0.02 multiplied by 0.05, which is 0.03625 meter. So 0.03625 meter is from the bottom until the centroid of this total area. So 0.03625 is the neutral axis for this shape. Okay, for the third one, we need to calculate is the moment of inertia. So the formula for moment of inertia for rectangular only is 1 over 12 bh cube plus ay bar ay square. So y is also the centroid of this shape. I'm sorry. Y is the centroid of the shape, the distance from the centroid of the shape until the neutral axis. So 12 multiplied by the base of the for this one is shape number 2 for area 2. So it's 1 over 12 multiplied by 0.05, 50 millimeter, multiplied by 0.02, 20 millimeter, cube, plus 0.05 multiplied by 0.02, the area, multiplied by 0.0365, this area, from this area until this area, minus 0.01. 0.01 is because the centroid of this shape is 10 millimeter, which is also equals to 0.01 meter. So the y, this one, area is this one. The y for this one is 0.03625, this whole area, this whole length, minus by this length. So the y is this one. Okay, for section 1 is 12 multiplied by 0.02 multiplied by 0.07 cube plus 0.02 times 0.07, the area, multiplied by 0.05 minus 0.03625. The centroid of this shape is 0.05, which is we calculated just now, here until here, 0.0255 minus 0.03625. So we only left with this area. I mean this length. So y is this length. And then we need to square it. And after we calculate it, we will get 1.8 times 10 power of negative 6 meter power of 4. So this one is our moment of inertia. So the next one we need to calculate is the Q from this one, Q. So we already have moment of inertia and the shear force. So the moment of inertia is 1.8 times 10 power of negative 6 meter power of 4. So the Q, for Q, we need to calculate the area of this shaded region. So the area prime is this area, which is 0.05 multiplied by 0.02, 0.5, 0.05, 0.02 multiplied by the distance from neutral axis until the centroid of this shape, shaded region. So it's 0.03625 minus 0.01. So after we calculate it, we will get 2.625 times 10 power of negative 5 meter cube. Okay, so our Q, we already get our Q, which is 2.625, sorry, 2.625 times 10 power of negative 5 meter cube. Okay. So the last one is T, width of the member cross-sectional area measured at the point where tau is to be determined. So the point we need to calculate is B. So from B we can find the width of T is 0.02 meter. 0.02 meter. So our T is 0.02 meter. So we already get our V, I, T, and Q. So we just need to put into our formula where the shear stress at point B is equals to 6 times 10 power of 3, because we need to convert 6 kilonewton to Newton. So we need to multiply it by 10 power of 3. So this one. So it will become Newton. Multiply by 2.625 times 10 power of negative 5, our Q. And then I is 1.8 times 10 power of negative 6. And then our T is 0.02. After we calculate it, we will get 4375000 Pascal, which is also equals to 4.38 megapascal. So the shear stress at point B is equals to 4.38 megapascal.
Okay, now we will learn about the shear flow in a build-up member. Firstly, we use this formula. V is this shear, and Q is this Y is distance from the natural axis to the centroid of A, and this A is the area, and this I is the moment inertia. After the calculation, we calculated that I is this answer and Y is this answer. This is from the top. Then V and the Q this one is the natural axis, to the center of this spread, this distance, and this is area of this. Then I is this one. Then the answer is 49.997 kilonewton per meter. Lastly, we use this formula. You can see that this S is the spacing between the board, and this Q 49.997 and 0.25, and the final answer is this. It's so easy. Thank you.